Hello everybody, and welcome to chapter 8 and last chapter of our nanoelectronics course. So in this chapter we are going to explore solid state memories, and more in particular the floating gate non-volatile memory that we will see later on in this chapter. First of all, let me remind you what we mean by solid state memories. So solid state memory is a storage device that does not have any moving parts, any mechanical moving part. So for example, hard disks, CDs, DVDs, tapes, they don't fall in this category. A solid state memory is effectively a piece of silicon that is capable in some way to store information. And you may be actually quite familiar with this, as today the solid-state drives are becoming more and more familiar, and they are more and more common. So for example, in your tablet, in your smartphone, definitely you are not even given the choice of choosing between a standard hard disk with moving parts or a solid state drive. So you know already that there are solid state drives in there. One key thing to note here is that the field of information storage is effectively the only field that cannot be completely conquered by the integrated circuits. It was still a field where older technologies like those that related to standard hard disk drives were based upon. So it is only recently that solid-state drives have become, thanks to scaling and miniaturization, have become much more affordable. Since we are talking about information storage, please remember that the number we are talking about today in terms of storage capabilities are enormous. So just reflect on the fact that when you are talking about a 1 terabyte hard disk, effectively you're talking about 8 terabits. And so this means that 1 terabyte hard disk drive has to fit in 8 10 to the 12 memory cells, if we assume that each memory cell is capable of storing 1 bit of information, which will be either a 0 or a 1 in digital terms. So really we are talking of huge numbers, 8, 10 to the 12. And so think for a moment to the difficulty in addressing each of these memory cells, powering them up, and so on and so forth. So huge technical achievement, if you like, in making solid-state drives of this very large capacity available today. So as we mentioned previously, examples of solid-state drives are, pen drives, SD memory cards, the solid-state drives in your tablet, smartphones, and so on. We should remember also that, as I briefly anticipated already, solid-state drive, as any other memory device, is addressed through a matrix approach. So the memory cells are interconnected with each other in a huge matrix of elements, and each of these cells is effectively addressable by properly selecting rows and columns in this huge matrix. We will see this in a moment. And it is important to note also that the way information is stored depends on several factors, mainly the technology effectively. So it can be stored in terms of charge, resistance, can be stored in terms of magnetic state or some other important variables that could be applied. So let us have a quick look at how a memory array could be made. So in general, we could think of it effectively as a matrix with columns and rows. We will call the column lines bit lines, and sorry, let me use red, bit lines, and the rows, for example, word lines. The terms are not by chance chosen like that. The reason is that when we think in binary form, a word is effectively 16 bits. And so effectively in this matrix arrangement of my memory cells, when I select, for example, the word line 1, effectively I'm selecting, if my word is made of 16 elements, all the 16 elements that are along this line here. And so if I wanted to select just cell 1, I would activate, if you like, the word line 1, the bit line 1, and so in this way I'm effectively addressing just this cell 1. And so if I wanted then to change the second bit, I would then activate the other bit, and then so on and so forth. In this way I can for example, write, erase, or read the information in the cells that belong to the word line 1, and so on and so forth. So this is the idea behind this matrix arrangement of a memory devices. And this is actually used in many other type of configuration or devices and technologies. For example, LCD displays are built in following a similar approach. Now, but what is important here to note is that when we talk about the cell, it is very important to realize that in reality the cell is actually made of more than one component in general, and fundamentally it must contain at least two components. The first one is the selector device, and the second one is this memory cell itself. The selector device is of fundamental importance, and it is effectively the device that allows to separate properly or to select properly just the memory cell we are interested in. With this I mean that if we go back a moment to the previous slide, you can see here that when I activate WL1, effectively I'm selecting all the devices that are on WL1. So, for example, if by selecting I mean applying a high voltage on the line WL1, effectively that high voltage will go here, will go here, will go here, and so on and so forth. So it is important to make sure that in each cell there is actually a selector device that, unless BL1 is also selected, then cell 1 will never be selected. So it will never, whatever is in WL1 line will never pass into the cell unless both WL1 and BL1, for example, are on in the case of the cell 111. So this is the role that is played by the selector device. So the selector device is device that will look at the word line and the bit line it is attached to, and unless these two have been selected, then the memory cell remains untouched. The information is never affected. And obviously, you can already realize that the best selector device is actually the MOSFET. And the reason is that is a 3-terminal device that is immediately prone to be used in the way we are saying here. And basically the idea is, for example, to attach the drain to the bit line and the gate to the word line. And in this way you have immediately made a selector device, and then the memory cell would be attached to the source in this case. So this is very important fundamental information related to the architecture, if you like, of a memory drive and how it would work. Regarding now more in detail solid state memories, we can categorize them in two big groups. First of all, volatile and non-volatile. So volatile means that the information is lost if there is no power, while non-volatile means that the information is retained even if the power is lost. And actually the information is retained for up to 10 years. We will see this later on in this chapter. Now, regarding volatile memories, we will not deal with them in detail here, but it's important to just have an idea what they are. So you may be aware, may be familiar with this terminology. So there are two main types of so-called volatile memories, the SRAM and the DRAM. And then regarding the non-volatile memories, the fundamental one is the flash. So these three technologies represent effectively today the mainstream of memory devices. And in the rest of this chapter, we will deal in detail with the flash technology. Okay, before as you can see here on this very nice diagram, all these other technologies here represent what we are now researching into, so there are so many other technologies there that are being researched as a potential replacement of the flash technology, and so we will see some of these later on in this chapter. Just a few words on the volatile technologies that we've seen. So the first one is the SRAM, the static random access memory. This effectively is equivalent to a flip-flop. The information is stored as the state of a digital circuit that has a bistable characteristic, and this circuit is the flip-flop. So the flip-flop is a device that is made simply by transistors, as shown here in this nice schematic, and so it is the perfect example of a memory element that can be, because it's made simply by transistor, it can be directly integrated into microprocessors, and that's what we use today in the cache memories of our computers. So it is, and the reason it is used in this way is that it is very fast, but also it is very expensive to make. And so it is used in the cache memories because we need small cache memories generally. If you notice, cache memories are the order of megabytes or something like that. The other technology is actually DRAM. DRAM is actually extremely interesting because it is an extremely simple cell, but it is effectively, we could regard this, for us is very important because we could regard this as the predecessor of the floating gate memory, the flash, that we are going to discuss in detail later on. This is an extremely simple memory cell. It's simply made by a transistor, which is our selector device, if you remember what we said previously, and a capacitor. And the information is simply stored in the form of the charge state of the capacitor. So by operating on the transistor, we can allow the voltage levels that we set on the bit line and the word line to effectively be stored into the capacitor. In reality, it is obviously the value of the bit line that is being passed to the capacitor. So the capacitor is charged or discharged, and this effectively corresponds to the storage of information into this type of device. So an extremely simple device that is based effectively on the charging and discharging of a capacitor. So the dynamic of writing the information into this device or erasing information from this device effectively corresponds to charging the capacitor through some resistance that will be related to the resistor, to the transistor there, the selector transistor, or also the cables that are involved, and the same for the discharging. So discharging will be the discharge of the capacitor through some resistance, again the resistance of my transistor, and so on and so forth. So it is an extremely simple device. We know everything about it because we know how the transistor behaves, we know how it operates, we have a huge experience now on dealing with capacitors, so we can easily understand how this type of device works, and but most importantly, it represents effectively, as I said previously, the predecessor of what we are going to discuss in this chapter, that is the floating gate memory. So this is the first memory device, if you like, that and the simplest, that relies on the storage of charge. So let us have a look now at the flash technology, and more in particular to the device that the flash technology relies upon, which is the floating gate non-volatile memory. So the floating gate non-volatile memory was introduced in 1967 by these two gentlemen here, and at the time this was really a revolution, if you like, the floating gate memory. And the reason is also the beauty of the simplicity of this solution they found, because effectively the floating gate non-volatile memory is effectively a transistor. It's a transistor where in the gate stack we have introduced a floating gate. A floating gate means a piece of conducting material that is not connected with the external world. That's why it's floating. Obviously here floating is intended in the sense of electrostatic terms. The potential is not defined by any external electrode or contact. And it is only defined actually by the charge that we put on it. And that's what basically I'm saying here. So the information here is stored in terms of charge into this floating gate. So we've said that the floating gate non-volatile memory is effectively a transistor, so it operates as a transistor. So let us imagine that we use the transistor that we had a look at in chapter 7. So I'm effectively using here, as you can see, the same biasing approach. So imagine to apply a gate voltage of 5 volts and a drain voltage of 7. Let us assume that the source is at reference potential 0. And so in this situation, we attract minority carriers to in the channel region, and we create a channel that will be deformed, let's say, in the way that I've shown here because of the electric field between the source and drain. And on the output characteristic of this transistor shown here, this means that we would be in this point here shown in red. Effectively, we would be on this blue curve that represents the output characteristic of the transistor when VG is 5 volt. By this I mean that if we were now to imagine to change VD in this range, then we would move effectively over this curve. Okay, so that's what I mean. But with these biases that we've applied, we would be in this point here. Okay, in this situation, as you can see, we have no charge into the floating gate. So let us imagine now that we apply the so-called right condition. So what we will describe is what we will call a label maybe as a state 1. We store bit 1 into the memory device. So in this situation, what we do is we apply a quite large gate voltage, 15 volts, and we apply the reference potential on both the drain and the source. So in this situation, the large positive voltage on the gate, effectively what we'll do is we'll create an inversion layer in the channel region, but because this is a very large positive voltage, effectively we may induce the tunneling of some negative charges from the channel area into the floating gate. So effectively charging negatively this time the floating gate. If this happens, when we now try to operate again our transistor, as we described previously, so using exactly the same biasing protocol, 5 volts on the gate and 7 volts on the drain, we would see that the current now is lower that we get. Effectively, if we were to move VDS in the range 0.7, we would actually see that we are, sorry, let me change color because otherwise we won't see it. We will actually be describing this curve. The output curve would be this one. So you can see that now the current is generally lower. And the reason is very simple, because by charging the floating gate with negative charges, effectively we are inducing this negative charge in the floating gate is going to induce some positive charge in the channel that will annihilate a part of the negative charges that was creating the channel. And so there will be less negative charge in the channel. And so this means that the current will be smaller. And so that's how we can explain this, what we just said about the output characteristic and where we are with current. Let us imagine now that we do the opposite. So we do what we will label now as the reset operation. That is to effectively store the state 0 now into our memory device. So in this case, we to perform a reset of the device, now we apply 0 volts on both the source and the drain, but this time we apply a very negative gate bias. For example, imagine minus 15 volts. In this situation, what will happen is that we now are accumulating majority carriers. We are putting the MOS stack into accumulation. As you can see now, we have positive charges accumulated to the interface with the electric material, and if the gate bias is negative enough, then we could actually force tunneling of some of this positive charge into the floating gate, so effectively now charging positively the floating gate. And so in this situation, if we were now to reoperate again our transistor, we would realize that we would find ourselves up here. So the current now would be more than in the fresh condition when there was no charge. And the reason is that when there is this positive charge there, this will attract furthermore negative charges into the channel. And so this means that the channel will be effectively bigger than it would have been if there was no charge in the floating gate. And so this means that the effective characteristic that we would see for our transistor if we were to span VDS in this region 0 to 7 would be effectively this one. So anyway, more current than in the fresh situation. Oh, let me just remind you, I probably missed to stress properly these points, is that in the floating gate non-volatile memory, we have said that we are inserting the floating gate in the gate stack. And so now we define the bottom side, the insulator that is close to the channel region as the tunneling oxide, and while we define the top side of the insulator of the stack as the control oxide. And the naming is exactly there to indicate the fact that in this region is where we expect tunneling to take place, while this is the region where we don't want any tunneling to take place. Okay, so let's go back to our floating gate non-volatile memory device. So we've now realized that by placing positive or negative charges into the floating gate memory device, effectively what we do is we are affecting the amount of current passing through the device simply by electrostatic arguments. But if we remember, the fact that my transistor is passing more or less current effectively depends on the transfer characteristic. Or to be more precise, because here we've always been using the same biasing condition. So VD is always 7, VS is always 0, and VG is always 5. But depending on the charge that we put on the floating gate, when the charge is positive, we were up here. When the charge is negative, we would be down here. And when there is no charge, we would be here. So effectively, what we are actually doing here for this to happen is that we are modifying the threshold voltage of the transistor. We are shifting the transfer characteristic of the transistor. This is what is really happening, and we can visualize this in the next slide. So as you can see, for a fixed VGS, if we remember, we've said that generally we measure the transfer characteristic at low VDS. And so if we were to again obtain the transfer characteristic this time of our transistor using a small VDS for the three charging states we've just seen, so positive charges, no charges, and negative charges, then we would see that the transfer characteristic actually would look like that for our NMOSFET transistor that we've seen previously. And so this means that this value here would be the V threshold for the reset condition. This value here would be the V threshold for the write condition. And so we can here effectively realize that by manipulating the amount of charge into the floating gate, we are changing the V threshold, the threshold voltage of my transistor. And so by measuring, if you like, the threshold voltage of my transistor, I can understand what information is stored in my memory device. The parameter that is extremely important then in this type of memory device is the separation between the two states, translated into a separation in the or maybe a shift of the transfer characteristic. And so it is effectively this delta V threshold that identifies with the separation between the two states. Please remember that how much charge we put into the floating gate, either positive or negative, will further modify the V threshold. So if we put the more positive charge, for example, we put, the more this characteristic will move in that direction, and the more we put a negative charge, and the more this characteristic will move in the other direction. So please remember that obviously these threshold voltages we are talking about obviously depend on the amount of charge in the end, on the absolute value, on the sign, and obviously the magnitude of the charge we are putting. And just to quantify now these things, how much is this delta V threshold we are talking about? So if we put some charge into my floating gate, how much do we expect the threshold voltage should change? Well, we've seen this formula again and again also in the past. We've seen it in several forms, and we see it here again. And the formula is obviously always this one here. So when we put some charge inside an insulator, then this will, an MOS device, then we should expect that this charge will cause changes in the flat band if it is an MOS capacitor, or changes in the threshold voltage if it is a MOSFET transistor. And so the formula is always the same, so it's minus gamma Q, the charge, or delta Q, over Cox, where Cox is the capacitance of the oxide stack. Where gamma, remember, is this one here. In reality, well, remember that we've in chapter 4 we have defined gamma as X over Tox, where Tox was the total thickness of the insulator, but and where X is actually the distance between the point where the centroid of the charge and the metal gate. So by using the formalism we've used here, X is effectively DCO, so the thickness of the control oxide, and Tox, the total thickness of the oxide, is DCO plus DTO, so the thickness of the control oxide plus the thickness of the tunneling oxide, and where Cox is the capacitance of the whole insulating stack, so the control oxide and the tunneling oxide, and comes down effectively to this formula here. So by substituting things in, we can conclude that the formula is actually in its simplest form, this one here. This is assuming that tunneling oxide and control oxide are made of the same material. If this is not the case, then we can demonstrate that actually the formula becomes this one here. If you want to double check this, you can simply go back to the formulas we used when we actually derived in the first place this formula here, and you can easily realize that indeed in the general case delta V threshold can actually be written like that. And if you notice, this quantity here is actually representing CO, the capacitance of the control oxide. So by realizing this, so the most general formula, if you like, that we could use is actually this one here. And just for fun, we could try to get some feeling of what these formulas means. To do that, we could, for example, say, okay, what is a shift in the threshold voltage that my instruments could detect easily? Just in terms of order of magnitude now, we could say that a reasonable value would be of the order of 100 millivolt. Okay, so 0.1 volts. And so if we assume, for example, that the control oxide is a piece of insulating material of thickness of 20 nanometers and is made of silicon dioxide, then we can easily calculate that the capacitance of the control oxide is 172 nanofarad per square centimeter. Oh, please note that in all these formulas, we don't care about the actual area of the device. So everything can be considered here to be per square centimeter, or anyway per unit area. So the capacitance of the control oxide is 172 nanofarad per square centimeter. Here I'm assuming obviously that the dielectric constant, the relative dielectric constant of silicon dioxide is 3.9. And so by using now this formula here, I can calculate which could be the absolute value of the charge that would be able to cause this threshold voltage shift. And by doing the calculation, we realize that this is 17.2 nanocoulomb per square centimeter, that if we translate in number of elementary charges, we get a number of the order of 10 to the 11. So this is basically telling us that in most floating gate non-volatile devices, really in order to get start getting shifts of the threshold voltages of the transistor, it means that we are effectively putting into the floating gate 10 to the 11 or more elementary charges, either positive or negative. Okay, this is a number that it's nice to keep in mind as it may become useful later on. Oh, just to go back to the fact that this formula is the fundamental formula to use every time we put some charge, we insert, if you like, some charge into the insulating material of a MOS device. We can see that when we dealt with the MOSFET transistor in chapter 7, we've actually seen this formula in action. And if you remember, when we wrote down here the threshold voltage of the transistor, that we said was given by these terms here, you can actually see that the term related to the oxide charge is there. Remember here gamma is missing for some typo. So you can actually see why this term is there. At this point, it is also worth mentioning something that we may mention again later on, but I think it would make sense at this point since we mentioned chapter 7 and that formula we've just seen. So when we operate our floating gate non-volatile memory and we start placing charges, positive or negative, into the floating gate and doing tunneling, stressing the device and so on and so forth, definitely, as we've explained until now, the threshold voltage will change because of this formula here and because of what we've said here, because of this term. But remember that stressing a device can always cause other effects. And the simplest thing, for example, I could point to you just so that you are aware of that, is that by stressing a device, I can actually damage, if you like, the integrity of the materials. And this means, for example, I could modify DIT. As I'm operating my memory device, at a certain point, DIT could start increasing. This goes into the category of reliability issues. We will mention this later on. But so what I'm trying to say here probably is that in some cases the threshold voltage may change, not just because of the charge we are placing or storing into our cell, be it a floating gate or any other charge-based device, but because probably we are modifying something else as well. So keep always in mind that it is important to know what other things may be affecting the parameter you want. So in our case, through placing charge into the floating gate, we are hoping to cause threshold voltage changes. But remember that this kind of operation can cause also other things that also can affect the threshold voltage. So, things can get very complicated very easily. Okay, let's go back to our non-volatile memory device, floating gate non-volatile memory device. Let us have a look now at what is happening from the quantum mechanical point of view. So we draw here our energy diagram of the gate stack now. So we see the silicon channel region here, the tunneling oxide, the control oxide, the gate, and we've explicitly written here that our floating gate is actually made of polysilicon. This was obviously shown also in the previous slides. I forgot to stress this point, but polysilicon is used anywhere where in the semiconductor industry where there is a need for effectively a metal. The nice thing is that this is a metal that is effectively just made of silicon. And that's why the semiconductor industry likes to use it a lot, at least until some time ago. So the floating gate in any floating gate non-volatile memory device is actually made of polysilicon, and we can consider this as a metal effectively. So when there is no bias applied across the gate stack, the energy diagram looks like that. So just remember that normally for these few slides we are assuming that TO and CO are effectively silicon dioxide. So the barriers, for example, between silicon and TO is of the order of 3 eV. It's important to remember this because, as we said, these devices will rely on Fuller-Nordheim tunneling. So, as we will see in a moment. So, let us imagine now to apply, as we said, the conditions that we used to write. And we said that in order to write, we apply a large positive gate bias. So this means that the gate side is pushed of the energy diagram is pushed downward really a lot until some electrons from the channel region that the channel is in inversion, remember, so there are a lot of electrons here, and so some electrons can be populating now the floating gate. And so this is now the floating gate is charged negatively now by Fuller-Nordheim tunneling. Obviously also direct tunnel could be at play, but generally things are tuned in such a way that this device will, the Fuller-Nordheim tunneling will dominate. So, and effectively we can see what we just said about direct tunneling or Fuller-Nordheim tunneling here, where we see how the energy diagram changes as we increase the gate voltage, and so we push down and down the gate side of the energy diagram. And so as we can see, we go from the light colored energy diagram, we go from direct tunneling, which is tunneling through a trapezoidal barrier, into basically on this one, in this case here, the barrier now, as you can see, is now any more triangular, and so in this case we have Fuller-Nordheim. Now, how can we characterize the operation of such a device that is based on the storage of charge into the floating gate that then, as a result of the charge, will change the threshold voltage of the transistor? The best way is to use this memory charging characteristics plot that I've shown you here, where we effectively plot the threshold voltage that we can extract from the transfer characteristic of our device for each given gate bias used to charge the floating gate. Oh, please remember, I didn't stress this enough probably, but it's obvious that when we say we do the write operation or erase operation, this is done applying a gate voltage for a certain amount of time. So effectively we are applying a pulse, a gate pulse, and that's what we are plotting here. This is the absolute value of the gate pulse height. Absolute value because when we want to do a write, in this case we apply positive pulses. When we want to do an erase, we do negative pulses, negative voltage, as indicated here. So as you can see, this plot is made of two branches that I shall probably better color in red and green. So for example, this red part is the one related to positive gate pulses, where we inject electrons, negative charges. And the other one, this one here, is made of, by using negative gate pulses. So we inject this time holes or extract electrons. Anyway, we charge positively the floating gate. So I think what is worth, there are several things that are very interesting in this type of graphs, but for the sake of our exploration, let's say, of these devices, one important thing is really crucial here, and that each branch goes through a maximum and seems actually saturating anyway. So what is important here is this fact that, you know, the branch won't keep going forever. It will saturate. So, and it is very important to understand why this is happening. And the reason is that we need to remember that this device, the gate stack effectively, is made of two parts: the tunneling oxide, the control oxide, and that the charging process is effectively a dynamic process. So as we said, we apply a pulse for a certain amount of time. Plots like the memory charging characteristic that I've shown here are actually obtained for a specific value of the write pulse and the erase pulse. So we should actually specify here which was the write pulse duration and the erase pulse duration. And so this means that we have two more variables to deal with. Okay, so remember that the charging is a dynamic process. In this case, is related to tunneling and so on and so forth, but it nevertheless happens in a certain amount of time. And so we need to keep in mind the variable of time here. Okay, and especially the fact that for the specific case of our floating gate non-volatile memory device, that we know that when we start charging a point in an insulator stack of a MOS device, that point will change its electrostatic potential energy. And that is at the heart, if you like, of this saturation process. So in order to understand this point, what we need to do is have a look at what happens to the energy diagram at the start and at the end of any gate bias applied to my device in order to store some information. For example, let us imagine that we are applying a gate biases of 4 volts. So in blue, we show the energy diagram at the beginning of the application of these 4 volts and at the end of the pulse. Obviously, we know that from the memory charging characteristic that when we apply 4 volts of gate bias, there is no change in threshold voltage. And that's what the energy diagram is showing us. The charge that we probably putting here, now I'm indicating that there is no tunneling. Probably there is some tunneling, but simply the charge we are putting here is probably too small to cause any detectable change in threshold voltage. Remember, we've said that for the size of the today's non-volatile memory devices, where the insulating stacks are the order of maybe 10, 20 nanometers, we calculated a few slides ago that the amount of charge we should expect to put into the floating gate in order to have a measurable change in the threshold is of the order of 10 to the 11, of more than 10 to the 11 electrons per electrons or elementary charges anyway per square centimeter. Okay, so if the charge that is going here is smaller, much smaller than that, we just cannot appreciate that change. Okay, so in this sense, please read this X I've put here. So tunneling is always taking place, but probably not at a level that causes measurable changes. So we can, in very good approximation, assume that the energy diagram in this case doesn't change effectively. When we then, though, go to the situation where we apply 11 volts, plus 11 volts, so we are injecting electrons, we can assume that at the beginning, the blue diagram is this one here. Obviously, you can see that there are straight lines everywhere because we are assuming that initially there is no charge in the floating gate. But at the end of the pulse, there will be some charge. And so the presence of the charge now must be measurable because we are measuring a change in the threshold from the fresh situation. The fresh situation is represented by this the threshold here. And so this means now that the charge we are sending into the floating gate is more than 10 to the 11 elementary charges per square centimeter, maybe 10 to the 12. And so this means now that in this case we are putting electrons, we know it, so negative charges, and so the energy diagram in this point has been pulled up, has to be pulled upward because of this the presence of these negative charges there. We found out, if you remember, some time ago, that when we place negative charges in the energy diagram, basically the energy diagram is pulled upward. And so this effectively means that if at 11 volt we had a good amount of tunneling taking place, which is highlighted by this blue arrow here, well, now it may not be the case anymore, or it's definitely reduced, because as you can see, the red, this the red energy diagram here has a much smaller slope. So this is indicating that the electric field in the tunneling oxide is now smaller. So at the end of the pulse, the charging effect of the flooding gate has the effect of reducing effectively the electric field in the tunneling oxide, while it is the electric field in the control oxide that is actually increasing. And so it is possible that at this point, because we are still, you see, in a region of my memory charging characteristic where we are the threshold voltage can still further increase if we keep increasing the gate pulse height. But I believe, again here, read this X cross, the cross that I've put here as, that there is very little tunneling taking place. But as I said, this is, this is a dynamic process. So there will be actually some, the more we move forward in this process, the more the charges that are in the floating gate will start to tunnel now through the control oxide toward the gate. And it is actually this that happens when we reach then the saturation, let's say, of the charging process. So, for example, when we use much larger gates values, like 14, we charge so much during the pulse, the floating gate, that then the charge we placed here is now so large that the electric field in the tunneling oxide is now become extremely small, so we are reducing enormously the tunneling taking place here, but now we are facilitating the tunneling through the control oxide. And so when we are effectively, beyond this maximum that I've indicated now here, it means that we are effectively facilitating the tunneling through the CO, to the control oxide. Now, it doesn't matter too much in this case. This is quite a complex situation that I've picked here, where the memory charging characteristic seems also to go down. We don't want now to investigate this specific issue here, but in our mind, what is important to note here is that the threshold voltage increases and then it stops effectively. So imagine this situation, that is the situation we are discussing here. So that the threshold voltage will saturate at a certain point. And the reason is this one, is effectively the fact that there is an equilibrium between the tunneling current through the tunneling oxide and the tunneling current through this control oxide. And at a certain point, we reach an equilibrium. And this means that the charge into the floating gate cannot go beyond a certain value. And so, just to put this dynamic process we've described in a bit more formal way, what we've effectively described up until now, if we call, ITO the tunneling current through the tunneling oxide and ICO the tunneling current through the control oxide, what we're describing effectively is the continuity equation for current, which is this beautiful equation here in differential form, where the gradient of J, which is the current density, which we could assume is a three-dimensional generally vector, must be equal to minus the rho dt, where rho is the charge density in that specific point we have considered. Put in this form doesn't seem too appealing to our specific situation, but we can put it in an integral form and immediately becomes much more useful, I think. So we can see that the equilibrium we were talking about between the tunneling current in the tunneling oxide and the tunneling current in the control oxide is actually well described in this formula. So the difference between these two currents is represented by the variation in time of the charge in the floating gate. So if there is any difference between these two currents, we are effectively modifying the number of charges into the floating gate. That's what this formula means. What we've said until now describes the operation of a floating gate non-volatile memory, so how we write, how we erase, and what it means when we write, and what it means when we erase, and the general, let's say, injection and extraction process of charges from the floating gate. But the floating gate non-volatile memories is an incredible device that has been there already for nearly 50 years. And they still remember the mainstream technology for non-volatile solid state non-volatile memory devices, and so it has to fulfill other fundamental requirements if we are to use this device as a non-volatile memory device. And the requirements are obviously in reality many, but here we want to deal with the two fundamental ones that are these two that I've highlighted here. So the first one is that for any memory device, when we say that it is non-volatile, globally we accept the fact that this means that the states that can be stored into this device remain well distinguished for at least 10 years. So this is translated into the fact that the retention time, as it is called, is bigger than 10 years. What it means technically, obviously, this is another matter, but for now, this is the definition. And the second point is that non-volatile memory device is a device that we will use and reuse continuously. So it must have some reliability built in it. And so the device has to be able to withstand at least 1 million of write and erase operations. So this is called the endurance of the device. So endurance to write erase cycles has to be bigger than 10 to the 6. And here below you see two graphs that are generally used to highlight this type of or maybe to demonstrate that a specific device has what it takes to be categorized into the non-volatile memory category. And so, for example, here you see a retention measurement that is done simply by writing the device, by performing a write operation, and so that the threshold voltage of the device goes here, and then we monitor in time the state of the device. Oh, please remember that I didn't stress it previously, but once we write the device, the way we monitor the state of the device is simply by effectively measuring the transfer characteristic and getting the value of the threshold voltage. So that's what we are doing in this type of measurements, at least here. And so when I said that we monitor in time the state, we monitor the threshold voltage. And so, for example, in this case, we see that this device was measured for up to 10 to the 5 seconds, and then we can extrapolate. There are obviously models there that somebody can use, and so on and so forth. But anyway, this is a different story, and they're extrapolated. Obviously, the data are extrapolated to 10 years, and the same for the erase state. So you can see here that when you charge the device to the erase state, and then you monitor the threshold voltage and so on. Before we move to the endurance, let me just mention how we read. Once we store information in the device, how do we read our device? So the simplest way to do this read operation is to effectively say to do, sorry, let me find the diagram, is to effectively look at this diagram. And so what we could say is that in read operation, we always bias the device with a VG 5 volts, and we apply a VDS of 7 volts. If the current I get is 5 whatever units is there, then we know that we are in we've stored a 1, or if we are in the current we get is I don't know, 15, this means that we store a 0. Obviously we need to include there some ranges. It's not just, you know, a single value. So we could say between 10 and 20 we are storing a 0, between 10 and 0 we are storing a 1, and so on and so forth. So this could be a way to read the information stored in the device. Going back to now to the endurance measurement. So in the endurance, what we do is we perform sequentially write and erase operation continuously, and every time we monitor where is the V threshold of the device. So in this type of measurement, the idea is effectively to check that ideally the V threshold for the write and V threshold for the erase shouldn't change, ideally. So because here we are using always the same writing and erasing conditions, so ideally we are charging the floating gate always with the same amount of charge. If we see any problems with the stability of the V threshold, means that we are effectively going back now to what we said previously about chapter 7. This effectively, we could be causing other problems to our structure. So for example, we could be creating damages into the insulating layers. So if we look at this formula, for example, the easiest thing to say could be, oh, maybe we are generating some interface traps, for example, or so on and so forth. So I just want to say that problems that show up here in terms of a non-flat V threshold for the write or for the erase indicate reliability issues within the structure that needs to be addressed. Okay, so that's the idea. Oh, just in terms of formalism or labeling of things, in the retention measurement, which is obviously, as we said, one of the most important measurements that someone should do to check that the device is non-volatile, we use the separation between the write state and the erase state in terms of threshold voltage is generally called memory window of the device. And so in this case, we could say that the memory window goes from 2.9 volts, that is at the beginning of the measurement, down to 2.3 volts, which corresponds to, I don't know, 80% of the memory window in 10 years. So that's the way that people look at this type of measurements. Okay, let's now have a look at which are the problems that arise when we try to scale down the floating gate non-volatile memory. Obviously, except those problems that we already know that affect the MOSFET, because obviously remember that the floating gate non-volatile memory is effectively a MOSFET. So the problems we will deal with here basically are those related to the gate stack. And so the first one is how to lower the operating voltage, for example, but keeping the capacitance of the device constant? We've come across this type of question before, and so we will see in a moment why we are saying this. The second point is the leakage through the insulator. So as we scale, we should expect problems of leakage through the gate stack. The third one is what do we do with scaling the floating gate? And the fourth and last point is the capacitive coupling between neighboring memory cells. So let's start with point 1 that is actually also related to point 2. So effectively, with what we say here, we will effectively be dealing with both points and proposing maybe a solution to both points. So the way people have addressed point 1 and 2, so how to decrease the operating voltage of these devices, is to effectively use mixed dielectric stacks. In the example we've seen previously, when we were trying to understand the operation of a floating gate and volatile memories, we've seen that there may be very large voltages involved. I've used, for example, 15 volts, but these are really true values for standard floating gate and volatile memories to be used. So we really want to decrease those. These are high voltages when the device is in the nanoscale. So we don't want to use such high voltages. So we need to come up with ideas. And one idea that has worked quite well for quite some time is actually to use mixed dielectric stacks. So the idea is effectively to use different materials for the tunneling oxide, the control oxide. The tunneling oxide to be, for example, silicon dioxide, and the control oxide to be a high-K material, for example, hafnium oxide. A good, remember, the key here is that has to be a reliable high-K material. We've mentioned at this point that we want to decrease the voltages, but we want to keep the capacitance unchanged. And so let us imagine, for example, I have my floating gate technology that is based all on silicon dioxide, both for the tunneling oxide and the control oxide, and I want to now shrink this device, and so I shrink both tunneling oxide and control oxide. But at this point, I realize that I have a problem. That this device will have a new capacitance. This will be the capacitance that I will use for my entire technology node. But I do realize that this, when the device is so small, there are problems. The voltage that I would use would be too high, and I would have leakage problems, and so on and so forth. So I need to find a way to keep the capacitance the same, but also reduce the voltage. And that's why this solution is so good. We will look into this in a moment, but here I wanted to stress the point of the capacitance. So when we change something, remember we've done this also with the transistor, when we change something within my technology, I need to make sure that the capacitance stays the same of the gate stack. And the reason is that in this specific case, my non-volatile memory cell is in a matrix, and that there are resistances it is connected to. The gate stack effectively is a capacitor, and so immediately I have an RC circuit that has some time constant, and this time constant I don't want it to change within my the same technology node. So I want to keep this time constant the same, because the time constant affects the response time. So if it was to be changed within the same technology node, it would create catastrophic problems. You can imagine from devices and devices. So we don't want to do that in general terms. So we always aim to keep the capacitance within the same technology, the capacitance at least the same. So this solution of using a mixed dielectric stack is good for both points 1 and 2, so reduces the voltage and keeps the capacitance the same, and also will reduce the leakage current, as we will see in a moment. That's what we've just said. Let us see why. So the reason why the mixed dielectric stack solution reduces effectively, helps in reducing the operating voltages of this device is because of very simple electrostatic arguments. So we can demonstrate that if delta V is the voltage we're applying on the gate, the voltage drop across just the tunneling oxide, which is the silicon dioxide, is given by this formula, alpha times delta V, where alpha is the gate coupling factor, while the voltage drop across the high K part is given by this formula here. How can we demonstrate this? Well, we've actually already done that, and we've done this. If you go back to chapter 4 and you watch what we did there, effectively we at a certain point we analyzed one a capacitor, and we came up with something like this, and we demonstrated that if you have two capacitors, capacitor 1 and capacitor 2, connected in this way, and you want to find out delta V1 and delta V2, then effectively delta V1 and delta V2 are given by these formulas, as simple as this. So please go back to chapter 4, we've done this there. Now we can straight away apply these formulas in our case. So in our case, our gate stack is the tunneling oxide followed by the control oxide, and you can see here I put a conductive piece of material connecting effectively the tunneling oxide and the control oxide, because there is the polysilicon material there that is effectively a metal, we said. So this is effectively the equivalent circuit of my gate stack, and so we have our VG voltage applied across this stack. Delta VTO we call the voltage drop across the tunneling oxide, delta VCO the one across the control oxide, and so we can apply straight away these formulas to our case. We can easily demonstrate that delta VTO is given by this formula here, which we can write as alpha VG, where alpha is this thing here in the most general form, where you can see I've kept KCO and KTO separated, and also DCO and DTO separated, in the sense that K values can be different, D values can be different. In the special case where KCO and KTO are the same, then the formula can be simplified into to this much simpler form. And in the same way, we can demonstrate that delta V CO is this. So if we play a little bit with do some algebraic rearrangements, we can easily demonstrate from that expression of alpha that we can write down alpha in the way I've shown here, where E hot HFO2, remember, is we've come across this quantity before, is called the equivalent oxide thickness of our hafnium oxide layer, and remember this is defined. Go back to we come across this in the previous chapters, is defined as this quantity here. So it is the actual thickness of the hafnium oxide layer, but multiplied by a factor that is related to the ratio of the dielectric constants of silicon dioxide and hafnium oxide, in this way that I've shown there. The beauty now of this approach is that using this approach, what we effectively achieve is that most of the applied delta V voltage will now drop across the TO. So when TO and CO, so the tunneling oxide and the control oxide, were the same material, effectively the voltage drop is proportional to the thickness of each of them. But now that we've changed the control oxide material to a high K one, then effectively we have another parameter to further play, and that effectively what we can use it for is to increase the voltage drop into the low K of the two, which is in this case the silicon dioxide, so which is the tunneling oxide. And this is important because this means that for the same gate voltage, I can now effectively apply more voltage on the tunneling part of my device. And this is the key. For example, let us assume that DSiO2 is 35 angstrom, so 3.5 nanometers, and D of my control oxide, that is hafnium dioxide, is 300 amps, so it's 30 nanometers. Well, in this case, if you do the calculations, you will see that 41% of the gate voltage will be effectively dropping across the tunneling oxide. 41%. If instead the entire structure was made of silicon dioxide, that number would drop to 10%. So you can understand why this is a magic trick effectively. It is an absolutely amazing technique to manage to lower the operating voltage of these devices. But also the use of high-K materials, as we've seen, some time ago, also helps in reducing the leakage, because we've said that in this transformation from standard silicon dioxide insulating layers to a mixed dielectric stack, we need to keep the capacitance constant. And so this means that the thickness of the hafnium oxide that I need to use has to be such that the capacitance of the control oxide effectively remains unchanged in this transformation process. But we've seen, go back to chapter 7, I think, or anyway, in the previous chapters, that the introduction of high-K materials effectively means that if we go from, for example, an insulating layer that is made of silicon dioxide, that is, for example, 10 nanometers, and now we want to move to hafnium dioxide, then this hafnium oxide thickness required to have the same capacitance will be much bigger, say, I don't know, 6 times more in the case of hafnium oxide, so 60 nanometers. And this means that if I had the leakage problems through my silicon dioxide that was 10 nanometers, now probably with my 60 nanometers of hafnium dioxide, I won't have any more such problems. And so that's why with this mixed dielectric stack, we solve also the leakage problems through the gate stack. The third point is how to replace the flooding gate. Technologically, I didn't mention this previously, but technologically the flooding gate, which is generally made in polysilicon, has a major problem when it comes to scaling, and that polysilicon is difficult to make thin. It's generally of the order of hundreds of nanometers. So getting rid of polysilicon in order to scale the device into the nanoscale, it is quite a challenge. So the only way is effectively just to you cannot scale polysilicon. You need to remove it and replace it with something else. And this something else is generally two things people have come up with, at least, is nanoparticles or a charge trap layer. So when we're replacing the flooding gate with nanoparticles, effectively what we do is we are hoping that the charge now will not be stored anymore in this big piece of polysilicon, but now will be stored in each single nanoparticle. So each nanoparticle is a storage node, if you like. We'll take some of the charge that previously was stored in the entire piece of polysilicon. This technology is used and has been used recently. For example, we know that Micron Technology, one of the major manufacturers, major players in non-volatile memories, is actually produced a floating gate non-volatile memory device based on nanoparticles in the 90 nanometer technology node. There is, though, a big problem with using nanoparticles, and one problem is the poor control on nanoparticle size. So remember, the nanoparticles are always confined structures. The properties, the quantum mechanical properties of these structures is heavily dependent on size, and so since we cannot technically make all the nanoparticles identical one to another, it's inevitable that we will have some particle size distribution. And so this is a problem. Creates a reproducibility problem from device to device. Another bigger, probably even bigger problem is that when you shrink too much, or maybe the nanoparticle solution is problematic when we scale aggressively the floating gate approach. Because when the devices become very, very small and you get in the channel area, in the channel region, maybe in the gate stack, very few nanoparticles, for example, say of the order of 100, then you may have from device to device statistical fluctuations that again you don't want. Because it is very important to remember that in our memory array, all devices behave exactly in the same way. Because all devices will be then programmed using the same pulses and the same protocols. So it is very important that they behave exactly in the same way. They have the same threshold voltage and so on and so forth. If the number of nanoparticles is not the same, effectively means that they will take less charge, for example, or more charge, and so the threshold voltage immediately will be different, and so we don't want that. That's very bad. And there is another important issue that if you are to put nanoparticles, you also want, where the charge is being stored, you also want that these nanoparticles are far enough from one another, because otherwise charge may tunnel from one charge to the other, and this could drive to leaks in charge. And so there is this condition on interparticle distance that should be at least of the order of 2-3 nanometers. So these are all these problems are big technological problems for this technology. Nevertheless, as I said, there are many examples that have actually come to mass production and may probably be in your USB stick, who knows. Now, in terms of operation now, again, if we start charging the nanoparticles, as we've seen from our general exploration of how the floating gate works, we should expect some shift in the threshold voltage of the transistor. And if we, so remember the formula is always the same, delta V threshold, mu minus gamma, Q over and if we now specialize this formula in our case, when we have some, certain nanoparticle density, and we have a certain number of electrons stored in each nanoparticle on average, and the epsilon CO is the capacitance of the control oxide, and so on and so forth, and then we can demonstrate that the formula could be written in this way. Where note that if you remember, gamma is effectively x over Tox, if you remember. X is the distance of the centroid of the charge from the metal gate. So in our case, we could assume that the centroid of the charge is in the middle of the nanoparticle. So this entire distance here is effectively, let's say, the thickness of the CO up to this point, and then half the radius of half the diameter of the nanoparticle. And the reason why this formula looks like that is because we need to take into account the different dielectric constants. So you can demonstrate this by going back again to the way we've demonstrated this formula here, or the formula. We've actually demonstrated this formula way back in chapter 4 when we calculated delta VFB equal to minus gamma Q over COX. So this formula can be easily demonstrated if we go back there and we take into account the new situation here. In the case though of nanoparticles, we need to take into account the fact that nanoparticles are possibly objects that are prone to confinement phenomena, and so to Coulomb blockade. And so this effectively means that in presence of nanoparticles, we need to take into account the fact that possibly each time we put an electron or anyway a charge onto my nanoparticle, a single elementary charge, the actual potential energy of my nanoparticle can dramatically change. And if you remember, we've seen what Coulomb blockade means, and we've actually looked into that. So if you remember, this is the capacitance effectively of a spherical object, in this case my nanoparticle, where TMP is the diameter of my nanoparticle, and then so we could we've seen at the time that every time we add one charge to the nanoparticle, the energy changes as a power of 2, and we can use that here to try to calculate how much the potential energy of my nanoparticle will change every time I add one more elementary charge to it. So we go from Ni to Ni plus 1. And so this calculation is done here, and as you can see, this goes with 2 Ni plus 1. This again is the results from the fact that the potential energy goes with the squared number of charges in the particle. And remember again regarding Coulomb blockade, the size of the particle is extremely important. As you can see, this is the potential energy of the nanoparticle with Ni elementary charges in it. As you can see, goes with Ni squared. And so if we have, for example, a 5 nanometer nanoparticle made of silicon dioxide, made of, in this case, I think silicon I've used, we can see that with one elementary charge in it, the potential energy would increase by this amount, 74 millieV. When we put 2 charges, the potential energy would go 296 millieV, as compared to the situation when there was no charge, of course, and so on. But if the nanoparticle is much smaller, so Coulomb blockade is much stronger, then you can see that the numbers become very quickly much bigger. And so what this means is that if these variations in potential energy are from one situation and the other are bigger than 3 kT, for example, at room temperature, 3 kT would be of the order of 75 millieV. So if these change variations are bigger than that value, whichever is the temperature in the end, it doesn't matter, then this means that Coulomb blockade phenomena could become visible in my nanoparticle floating gate device. And this means that we could exploit Coulomb blockade to actually create multi-state, multi-bit as they are called, memory cells. So for example, at a certain voltage, all nanoparticles would be charged with one electron. Then up to a certain voltage, nothing else can be done because of Coulomb blockade. And then when the voltage becomes bigger enough again, 2 electrons go into all the nanoparticle, and so on and so forth. And so we can create multi-state devices in this way. So remember, when I say multi-state, for 1 bit of information we need 2 states. For 2 bits we need 4 states. For 3 bits we need 8 states. Okay, so please remember this point. Remember now that in this exploration of how Coulomb blockade could be used in nanoparticle non-volatile memories, we are still not considering, as we mentioned, you remember when we treated Coulomb blockade, we are still not saying anything about quantum mechanical phenomena. Remember that when the nanoparticle is a confined structure, so discretization of the energy level will or may be important. So it's not just Coulomb blockade in the sense of the electrostatic energy of the small spherical object, but we need also to take into account, and we are not doing it here for simplicity, but we need also to take into account that there may be discretization of the energy level at play that may be very well important. And just to visualize a bit more what I've just said about how Coulomb blockade could be used to create multi-state devices. Here I have the energy diagram of my hypothetical non-volatile nanoparticle memory. And this is here at zero bias. Let us imagine now that we apply a gate voltage Vg equal V1 that could be potentially suitable to cause an electron to be injected into the nanoparticle. It doesn't matter now which is the mechanism. We just say that there is a certain electric field at which this electron will do that. And let's say that V1 is enough. So the red curve here is showing us the energy diagram of my device just before the electron is capable of going into the nanoparticle. But as soon as the nanoparticle goes in, we get the green diagram here. So the energy of the nanoparticle now has gone up, because we have one charge now in the nanoparticle, and the energy diagram so is changing. And you can see that in the TO now, the tunnel epoxide, the electric field is not anymore as before. You can see that the red in the red curve, the electric field was much more intense. Now probably there is even no electric field here, I don't know, but and nevertheless another electron cannot go in. So this is the Coulomb blockade I was mentioning to you about, how we can exploit Coulomb blockade to create multi-state. And so at this point, if I wanted to send another electron in, what I would have to do is to increase Vg more, until I drag down again this nanoparticle energy, and then I allow another electron to go in, and so on and so forth. And in this way, what you end up with basically is that the memory charging characteristic of the non-volatile memory becomes a step function, as the one that I've tried to qualitatively show here. So we go from a smooth curve to a step function like that. And this is exactly the way you can create multi-state devices. So for example, if I'm using a gate pulse of say 12 volts, I will be putting my devices in this threshold voltage. if I use 14 volts, for example, I will be putting my devices at this threshold voltage, and so on and so on. So I can create many states reliably in this way. Obviously, the question then is, are these states satisfying the retention conditions and endurance conditions? That's another, obviously, question, okay? So the things are much more complex, but this is the idea. Okay, regarding point 3, another way of replacing the floating gate is by using, instead of nanoparticles, that was one of the options we just mentioned, we can use a charge trap layer. A charge trap layer, as the word suggests, is effectively a thin film material where there are many traps, and so traps that can take either electrons or holes or both. And this is an extremely very good solution that has been working for quite some time and is much more promising, I have to say, as compared to the other solution we just mentioned with based on nanoparticles. And in this case, the material is the device is much more scalable as compared to the other solution we mentioned. We've seen that with nanoparticles there are some issues when we attempt to scale down the device. So this solution is seems to be much more promising. In this case, if we specialize remember always general formula, delta V threshold minus gamma Q oxide trapped charge over Cox to the specific geometry of our new floating gate device, where you can see that the trapping layer is now between the tunneling oxide, the control oxide. Then we can demonstrate that the formula providing delta V threshold as a function of the trap charge is effectively, and the geometry of course, is actually given by this formula here. And these type of devices are actually in production. So generally a very good material that is used as a charge trap layer is silicon nitride thin films. Silicon nitride in its natural form would be Si3 and 4, but in order to have traps, we should take into account the fact that in general it won't be exactly stoichiometric, so there will be some defects in the matrix, and this makes this type of thin film extremely flexible, and people can actually engineer even the location in energy of those traps. So it's quite a versatile solution that is also extremely scalable. So the charge trap layer can be made as thin as we want, even few nanometers. So it is an extremely promising solution there. And finally, the other point we mentioned about it that is potentially problematic is the capacitive coupling between neighboring cells. So when we scale down our floating gate non-volatile memories, we are making the devices smaller, but also we have to bring neighboring devices closer and closer. And when this happens, what we effectively have is that there is some crosstalk electrostatically between the floating gate of one device, which is a big piece of, as we know, of conductor, effectively polysilicon, and the other floating gate. because these are two relatively big pieces of capacitors, of conductors, there will be the more we bring them together, the larger will be the coupling capacitance that we've indicated here as Cx, which means that if, for example, on the device here on the right, there is a certain charge Q, well, for the electrostatic coupling existing between these two, there may be a certain charge Q tilde negative that is going to appear on the other one. So it's this crosstalk that effectively is has devastating consequences for our memory array, because now it would seem that on the device on the left we would read some stored information, for example, when maybe there wasn't, and so this causes errors into the writing and the erasing process of information and the reading process of information. So this crosstalk is something that you really don't want. And so the solutions we provided, we've mentioned, for example, nanoparticles or use of charge trap layer, both go in the right direction of reducing the crosstalk, because, for example, in the case of nanoparticles, our storage nodes are now each single nanoparticles. So now really between this nanoparticle and this nanoparticle, the crosstalk, the capacitance, let's say, existing between these two will be basically negligible compared to at least the one that we would have had in this situation here. And so now the crosstalk can be effectively neglected, and things, the options that we've discussed in point 3 actually are extremely good also in solving, in a way, point 4. But definitely the standard floating gate approach with a single piece of conducting floating gate cannot be used when we attempt to scale down, also for this reason of crosstalk between neighboring devices. Okay, what we've seen up until now is an exploration of what we know about floating gate non-volatile memory devices, and the challenges and the options we have when we attempt to scale them down. It is clear, though, that the floating gate concept, although has been at the basis of, has contributed to the success of microelectronics and nanoelectronics, is clear that has some limitations in terms of scalability, and there are issues related coming directly from the issues we've seen with the MOSFET concept, and but also the issues that we've seen more particularly related to the floating gate concept. So there is clearly a need, as anywhere else in this field, to start looking also in other directions. And so there are new, as we briefly mentioned at the very beginning of this chapter, there are also new emerging technologies that are being investigated in the last maybe 20-25 years, I would say. And these technologies are extremely promising and extremely interesting, also because they are not anymore, some of them at least, not anymore based on charge storage. Some are thought to revolutionize actually the field of nanoelectronics. They are thought, for example, to be able to replace volatile and non-volatile memories at once. So here we will actually discuss two examples we've seen that there is really a lot of directions. There are really a lot of directions in when we look at what people are investigating in terms of non-volatile memories, future non-volatile memory technologies. But here we would like to focus on two simple and characteristic cases, and these are the phase change memories and the resistive random access memories. The first one is at the so-called prototypical phase. So these are devices that are entering or are soon entering mass production, while the resistive random access memories are still in the emerging phase. That is, we have effectively identified that these are very good, promising devices, but we need to clarify some of the properties of the mechanisms that are there that we still not fully understand. So let us start with the phase change memory first. The phase change memory, as also the ReRAM actually, is a memory cell that is based on a two-terminal device. So it is equivalent to a MIM, a metal insulator metal device. So it put two electrodes in between the active material. And so these type of devices are all extremely suitable to a very simple architecture that is the so-called crossbar array. We will see it in a moment what it means. The same is we will see for the ReRAM technology. And the mechanism in phase change memories relies on the phase transition of the active material in between the two electrodes. And so these are the devices where the information is stored in terms of resistance of the cell. So by when the material changes phase, we are basically changing the resistance of the device. These are devices where the information is stored in form of resistance of the cell, and the mechanism is that is behind the resistance change of this memory cell is effectively the transition between crystalline and amorphous and vice versa through Joule heating of the active material in the cell. And these type of devices also offer very good multi-bit storage capability. We've mentioned this point also for floating gate devices, if you remember. So it's something that obviously helps in terms of integration capabilities of these technologies, if you can put more than one bit on each cell. Remember that all materials have amorphous and crystalline phases, but in order to use a certain material in a phase change memory, there is a more stringent requirement because it has to be non-volatile, and so it is very, very important that the phase is actually stable over time. And so this immediately narrows down the type of materials that we can use to really not many as we may think. And we already know phase change materials that have been effectively used in CD and DVDs, and the only thing is that there the information was stored in the form of change in optical properties of the material. So there was the final result of this phase change when you were writing some information in one location of the CD or the DVD was to have some optical contrast before and after. and so the two phases have as a result a change in the optical properties. In the phase change material, the result of a phase change is in terms of resistance. And generally, the materials that are very good in doing this are these type of alloys. In this diagram here, we see a schematic of a typical phase change memory, and we can recognize here the two electrodes, the top and the bottom. The active material, the one that shows this phase change transition, and also we see here something that probably we didn't mention, of course, and we see here another layer that is quite complex in a way. So it's a film that has is effectively an insulator, but has built-in a channel where there is a heater material is called. So this is a material that can withstand high temperatures without being damaged. So this is a very important component actually of the phase change memory. So the idea is that you by applying a voltage difference between the bottom electrode and the top electrode, you're effectively passing a current through the heater heats up, and so transfer some of that heat to the neighboring phase change material, and so it can create phase change into this region here. And so this region can either become amorphous in one situation or can then be recrystallized, and so it is these two phases that then cause changes in the total resistance of the device. In this diagram instead we see how the device effectively operates. So when we want to read the state of the memory, we have to apply a voltage bias and read the current in such a way that the temperature stays down, as is indicated here. Is not too much. We don't affect the state, if you like. So we must make sure that the reading protocol we use, so the voltage we use and the current we read, are such that we are not interfering with the state of the device. So that's why in terms of temperature, we need to make sure that we are at a very low temperature. The material has itself a certain crystallization temperature and a certain melting temperature. So when we want to create a transition from crystalline to amorphous, we need to make sure that the voltage and the current we pass through the device is such that the temperature shoots up to above the melting temperature and then quickly is dropped down so that we quench the state and so the material remains amorphous. If we instead want to crystallize the material, what we have to do is we have to use polarization, use a voltage and appropriate current such that the temperature is at an intermediate level, just above the crystallization temperature, and keep it for a bit longer, and also make sure that the temperature is dropped slowly, as you can see here somehow. And this makes sure that then that amorphous bit of material can then slowly crystallize. So this is, in very few words, the idea behind this type of device. In this slide, we can see a bit more in detail what is the crossbar architecture. So as you can see, it's top electrodes that in this case are bit lines that run all the way through the memory array, and at the bottom the word line electrodes that are that run in the other direction, and then in between, at the intersection of all these lines, there is an active piece of material that effectively represents the memory cell. In this description of the crossbar architecture, there are, as usual, two elements, as we've understood from what we've said, some time ago at the very beginning of the chapter. So there is a selector, so a selecting device, and the actual memory cell. The difficulty in the crossbar architecture is to make sure that we can find a selector device that can operate effectively with just two terminals, because you can see here that the selector device has only a terminal here and a terminal here. It's a two-terminal device. We've seen instead that in the memory arrays that we discussed previously with the floating gate, the selector device is effectively a transistor, so a three-terminal device. So there is quite a lot of research also in what should be the selector device for a purely resistive now memory network. So remember that the new thing now in these new technologies is that this information is stored in the form of resistance, not anymore charge. And so here, if you were to create this crossbar architecture just with your memory cell in between, without a selector device, this would be a perfect simply resistive network with some variable resistors that depend on where the resistance depend on the state that has been stored, and so on and so forth. But it would be impossible to address in a purely passive resistive network. It is not possible to address just one single cell, because they are all connected through resistors. In other words, if I had this was one of the bit lines, and I had imagine the bit line is connected to two word lines. Every time that I put here some voltage and some voltage here, there are more paths that connect this bit line and this bit line than just this one, because in fact I can go from this bit line and to this bit line with this resistor, through this resistor, and let's say that this was probably my intention here, but in reality, in a purely resistive network like this one, there are actually many combinations, because I could also follow this route. It could go this way, this way, this way, this way, this way, this way, done. So this is just to show you that there is a problem with purely resistive network, and so with the crossbar architecture there is an innate problem that is called the problem of sneak paths. That requires effectively that we find a proper selector device. And this is as important as the research that is taking place into these new emerging or prototypical memory technologies. So keep that in mind. Anyway, the very nice thing about this type of architecture, if we can make them to work, is that they have a huge potential to actually become 3D, because now imagine here you can stack another layer on top, other electrodes and so on and so forth. So you could stack these things into 3D, become 3D actual memory arrays. And in this and the other thing is that this type of architecture is prone to create memory arrays with extremely small footprint. When we talk in terms of scaling scaling capabilities, or maybe integration capabilities of certain technologies, we consider the actual footprint of that cell. So in this case, for example, of the crossbar architecture, if we call f the minimum feature size of our technology node, so f squared is the minimum area of our technology node, then we could demonstrate or say that for this specific crossbar architecture, the footprint is 4f squared. We will see that different technologies that are more complicated or simpler, they may require more or less devices in order to create one single cell, and so the footprint may be different. So we may see, for example, that in the standard floating gate memory, the footprint would be something like 10 f squared. So this is because obviously there you have a transistor, you need a certain space, as we've said, for the floating gate that is quite big, and you need some other devices, and so on average the footprint is 10 f squared, for example. So this is just to tell you that people tend to speak in these terms when we want to quantify how big are these devices, or maybe how promising is a technology in terms of integration capability, or how small we can make it. And on this diagram here, we can see maybe in 3 dimensions, or sort of schematic of effectively our device, the one that we had seen here, where we can see, for example, that the electrode, this is the bottom electrode, is tungsten, and then we have the bit where, if you remember, is the heater. You see the heater is made of titanium nitride. This is an extremely good material, is a conductor effectively, but is extremely resistant to high temperatures. We will see that phase change materials don't require extremely high temperatures, maybe 150, 200 degrees, 300 degrees top. Degrees Celsius, but still, when you have to operate this device continuously, this, as we know, would pose enormous stress on the heater. So the heater has to be extremely reliable, and titanium nitride is considered one of the best in this. Then we have our active material, the phase change material that we said is the alloy, and then the top electrode here that again is made of tungsten. So here we would like now to have a brief look at how the device effectively operates. So we've said that in order to operate it, to write information, to read information, and to erase the information, we need to, in the end, use some voltage and some current. So let us have a look how that works. First of all, remember that for us, the set transition is the one that will make us transform the material from the amorphous phase into the crystalline phase, while we call the reset transition the one that will the crystalline phase, remember, is the one that is more conductive, and the reset transition is the one that makes the opposite transition, so from crystalline to amorphous, where the amorphous is the one that is less conductive. So effectively, in the amorphous phase, the resistance is large, while in the crystalline phase, the resistance is small. So that's what we are down to in the end. So, and that's what we've summarized here as well. And so what we expect is, if our device is in the crystalline state, so has been set, so we should see this IV. So imagine that we are effectively reading now the device, or in order to read, remember what we've said, we need to use very small voltages so that the current is small, so that the temperature produced through Joule heating is small, and so it's not messing with the state stored in the device. And while in the amorphous state, if we do an IV, we should get this slope that is much smaller, and so this is in very simple terms how we effectively read the two states. And in this diagram here is reminding us what we said also in the previous slide about the reset process and the set process, while here we see now two voltage sweeps from 0 to, say, 1.5 volts, where for a device that was initially in the amorphous state. These are the open symbols, and for a device that was initially in the crystalline state. And so these are the full symbols. So let us consider first the device where the material was crystalline. Initially, the material is made crystalline, so the device would come when it comes out of the factory, if you like, in its fresh state, is fully crystalline. And so we would get, if we were to sweep the voltage from 0 to 1.5, we would, for this specific case, we would be moving. I will use the red curve for the crystalline state. So we would be moving along this line. Now, when we reach relatively high voltages, the current also is quite large, and so the temperature in the device effectively may be going above the melting temperature. So at this point that we marked as a reset, what we may be doing is that if we at this point stop suddenly the voltage, the molten material will quickly cool down in an amorphous state. And so if now what we've managed to do in this way is effectively to reset the device. So we've created a high resistance state now, and so if we now repeat the measure, we were to repeat the measurement, we would, and we sweep again the voltage starting again from 0, we would now realize that we are moving down here. Now in this situation, so now we are in the high resistance state. If we reach a certain threshold voltage at this point, what we realize is that this threshold voltage is such that is able to initiate the phase transition process from amorphous to crystalline. So at this point, if we keep this voltage long enough, the device will slowly start to crystallize. And so we would see that we tend to move again to the set condition, to the condition where the resistance was low, much lower. So this is, in few words, the way this device operates. And if we wanted to read, we would just use voltages that are down here in order to probe the resistance of the two states. So if the device was in the set condition, so crystalline, I would probe and do a small IV into voltages that are down here. I would probe this resistance, and so I would say we are in the set state. Or if I was to do the same and get values that are down here, I would say that we are obviously in the reset condition, in the other state, high resistive state. So here, this just to clarify a little bit what we've said a couple of slides ago regarding what is required in order to set, reset, or read the device in terms of temperature, and how this relates effectively with the voltage pulses we need to apply. So, for example, we had said that in order to read the device, we need to use voltages that are not going to cause high temperatures. And so this means that our red pulse that we would use is, for example, if we go back and try to relate to the IV curve that we've just seen here, we could use around 0.2 volts in order to read. And so that's what I'm showing you here. If we wanted instead to, for example, set the device according to what we've said previously, so in terms of temperature, we said we need to make sure that the voltage is enough to create a temperature that is just higher than the crystallization temperature, and then that we drop slowly the temperature in such a way that the sample can crystallize fully. And so the shape of the pulse that I'm describing has to be like that, the blue one that I've shown you here. So, for example, in the case of the IV we've seen in the previous slide, I would have to go up to, say, something like 0.7 volts, keep it for a little bit, and then drop it slowly. And this would create the situation of this recrystallization of the material. While if we wanted just to reset the device, so we need to create, bring the temperature effectively above melting and quickly drop the temperature. So I need a pulse that is high, like 1.5 volts, and short in duration, so that quickly drops down in terms of ball voltage. So a very sharp pulse required to reset the device, so to go from crystalline to amorphous. So you can try to relate the things I've said here with the IV example that we've seen on this slide here, and understand how we read, how we set, how we reset this type of devices. On this slide, we are effectively looking at the same things, just in a bit more detail. Here you can see that I'm showing you also the resistance versus the voltage applied. So, but there is actually no additional information in terms of operation that we've not already discussed. And here I'm effectively explaining to you what I've told you already in the last couple of slides in terms of operation. So on how the voltage pulses have to be in the set, in the reset, in the read, in order to be able to operate this type of memory device. Now, as I mentioned previously, the phase change material has to be able to change phase at a certain temperature, hopefully not too high, so that it becomes not too prohibitive to achieve. And here we can see studies that are actually aimed to understand how different alloys behave and they change phase. So here you can see several different types of alloys here, and we take these alloys initially in the amorphous state, and we are effectively exposing them to cyclic process of increasing the temperature and then decreasing it, and at the same time monitoring the resistance of the device of these alloys. So for example, if we take the top one, the blue one, we can see that we start from here. So initially the resistance was this one here, 10 to the 4. When we start increasing the temperature, the resistance drops. There is some sort of transition here, and then when we reach 400 degrees, and then we start quenching, cooling down the material, we can see that the resistance then remains here. So this clearly indicates a phase transition from amorphous to crystalline. And you can see that the same happens for the other one. So what we need to now decide is which material we want to use, which one, depending on which temperature we are aiming at. So you can see here that there are alloys that can undergo the amorphous to crystalline transition at something close to 100 degrees, and other require much higher temperature, up to 300, 350 degrees and so on. So also there is an enormous amount of research, of course, obviously, into the materials that the choice of materials. This is also something similar to what we have seen previously. And just this is just to further stress that when we say transition from amorphous to crystalline, there may be more crystalline forms as well. So this is another thing to look into, and especially for multi-bit storage. So another degree of freedom to think about when we create this type of devices. And again, as a non-volatile memory, this type of device has to be able to, show good retention characteristics, good endurance characteristic, as we pointed out for the floating gate non-volatile memory. So here we see a characteristic retention measurement for some published work here, and we can see that in the case of a resistive memory like the phase change memory, in this case we don't plot obviously the threshold voltage as we did with the floating gate, but in this case we plot the resistance of the resistive state we are considering. So we have here the low resistive state and the high resistive state, and so the idea here is that we set or reset the device, we put it in either of the states, and then we just monitor the evolution in time of that state by simply reading it continuously. So remember that the read is always an operation that has to be done carefully in such a way that we make sure we are not interfering with the state. So we must be very careful there. This holds for any non-volatile memory, so also for the floating gate. I'm not sure if I've stressed that at the time, but it is true for any non-volatile memory device. And the same happens then for the other state. As you can see here, there is some degradation, let's say, of the state. There is one concern, of course, in this type of memory technology that is relies on heating. So the phase change memory is a device It is relatively power hungry because it is based on Joule heating, and so the immediate concern when it comes to scaling down the devices, and so trying to put more and more devices next to each other is do we have crosstalk here? So is there an issue relating to, if I operate if I'm operating this phase change memory here, will the temperature gradient created affect a neighboring cell? So that's a very important question to answer. And there is a lot of work actually in this direction, and it would seem, here we see a simulation work on the scaling capabilities of phase change memories. And in this work, they are analyzing the feasibility of isotropic scaling. So isotropic scaling means that we scale in all 3 dimensions. And so this means that devices, as we move from one technology node to the other, the devices will become closer and closer, effectively. And so the question is the temperature of the neighboring device going to be affected? Well, the answer is, according to this work, is no. As you can see, the temperature of the neighboring device, once we are operating the device that here is marked as bit 1, when we look at the disturbed device, the device that is related to the neighboring device, to the one that is being operated, well, the temperature, while we are hypothetically scaling down the device, is not really changing a lot. So it remains around, as you can see, 300, I don't know, 90 or 80 Kelvin, completely acceptable. And this, as you can see in this work, they went down to maybe, I don't know, 15 nanometer technology node. So it would seem that the phase change memory should be all right, according at least to this work. So finally, regarding phase change memories, what we can say is that definitely there are a lot of advantages over flash. For example, the phase change process is very fast as compared to the write and erase process based on charge that we had seen on flash. Indeed, if you look at this table and look at the, for example, the write erase time for flash, flash. We didn't discuss this, but there are two technology, NOR flash and NAND flash. It doesn't matter now. But if you look at the erase, write and erase times, they are, in the best case in the order of microseconds, but really they are in the order of maybe milliseconds. And so we can see that instead in the phase change, we are really into the nanoseconds. So a huge improvement there. These devices also have obviously a very good retention time, but one very good point about phase change memories is that they have a very good potential in terms of endurance. So compared to flash, where the endurance is of the order of 10 to the 6, here we are talking about orders of magnitude more. So a very, very reliable device. And in this also extremely low voltage. So you can see that there is quite an improvement there. And so the only drawback, I would say, in terms of phase change memories is that there is a concern over the use of Joule heating in terms of power consumption. These devices are extremely small, so in the end the power consumption is indeed extremely small. I'm not showing it to you here, but nevertheless, Joule heating is not one of the most efficient techniques to use. There is a debate there, let's say. One of the biggest challenges, though, is definitely the selector. This is true for every crossbar architecture. We've discussed thermal disturbance, and we've said that, you know, probably is not a big trouble, but nevertheless, this must be double checked in practical terms, and especially at advanced scaling, when scaling becomes really aggressive, you know, down to 10 nanometers or so. And indeed, this type of technology seems to have some concerns, seem to have some problems, when we discuss, you know, scaling down below the 10 nanometer mark. Okay, the other technology we wanted to talk about is also a technology that is based on resistance change. So information is also stored in form of resistance of the memory cell, and is also, you know, a two-terminal device, effectively like a MIM, we said, metal insulator metal, and this is the ReRAM, the resistive random access memory. The architecture also is potentially the crossbar array, and this time the mechanism could actually be several, but all are actually down to the creation of filaments, of conductive filaments within the active material. And also here there is a huge potential for multi-bit storage capability. This phenomenon, the phenomenon of resistance switching of electronic materials, is actually known for many decades, even centuries. And the only reason it was never exploited is because in order to, when the devices were very big, the amount of energy that was required in order to switch the resistance of a piece of material was huge. And so in the 60s, for example, at a certain point, there was some interest in this type of technology, but then it was dropped. Because of energy concerns. It is only today, you know, in the last decade or so, that people have now scaled down a lot the devices, and the devices are now anymore extremely small, that this technology is now seen actually as the potential replacement of all non-volatile memory technologies. There are a huge number of materials that can show, when biased appropriately, can show resistance switching. This can be semiconductors and insulators. So there are really, I would say, all materials can show some sort of resistance switching for one reason or another. The mechanisms that we will talk about here are mainly three. These are the mechanisms that are more well accepted, let's say, and these are these three here. So the VCM, or valence change mechanisms, the ECM, electrochemical mechanism, and the TCM for thermochemical mechanism. Remember that because here we are talking about materials that rely their resistance switching on the creation of conductive filaments within an initially pristine material. This means that normally this type of devices, when they are fabricated, they have to undergo what is called an electroforming step. So a procedure to create for the first time these filaments. make the way, if you like, for the filaments. So once the electroforming step is done, the device can then operate normally. But this is something to keep in mind. So there is also research in this direction for devices that resistive switching devices that do not require the electroforming step. So first of all, there are two types of switching devices when we talk about ReRAM, resistive random access memories, and it all comes down to the biasing required. So we will mention unipolar switching and bipolar switching. So in a unipolar switching, set and reset and read operations are all done using voltages of the same polarity. As you can see here, the IV, this is the IV plot of the device. As you can see, current on the abscissa and voltage on the current on the ordinate and voltage on the abscissa. So in the top plot where we are talking about unipolar, as you can see, there is the IV characteristics are actually mirrored when we go from positive biases to negative biases. We will discuss in a moment what is the operation there. And when we go to instead of bipolar switching, this means that the set operation happens for example at positive voltages, while the reset operation at negative voltage, or vice versa anyway. So the voltages of both polarities are required when we want to operate the device. So the simplest one to understand here is the bipolar switching. So as we can see, the material, for example, initially would be in its high resistive state. So if we are performing a sweep along this curve, imagine that we are moving, for example, in this direction. At a certain point, at a certain voltage, the material would create conductive filaments, and so would suddenly move from that IV characteristic to another one. When there is this would be the set operation here. So when there is a set transition, normally we use the instrumentation to limit the current of the final state we land to. So this CC is imposed by this is a current limitation imposed by the instrument. So we land anyway on a new state, and if we now sweep backward, sweep the voltage in the other direction, we would move along this IV line, so which has obviously a different resistance, as you can see, a different slope. And so, but when the voltage here reaches this value here, the filaments are destroyed, and so we drop now back to our initial state. And so we have here our reset transition. In the case instead of and also obviously remember again that if you wanted just to read this type of device, you would simply apply a small voltage, for example positive or negative, it doesn't matter, as long as it is small and that does not interfere, is not bigger of any reset or set voltages. So you would apply a small voltage. If you get a current that is of this level, you would say I'm in the high resistive state, or if you get a current that was this level, you would say I'm in the low resistive state. Obviously, the larger is the difference between the high resistive state resistance and the low resistive state resistance, the better it is. So we need to make sure always that the states are as separated enough so that we can distinguish the states. When we instead have to deal with a unipolar device, so let us consider for a moment, for example, just the positive, the first quadrant here. So in this case, let us assume, for example, again that the material is initially doesn't have any filaments, so the material is initially in the high resistive state. So if we were to sweep the voltage and measure the current, we would move, down here a very small currents. At a certain point, when we reach a certain voltage, we set the device. Again, we use the instrumentation to limit the total current passing through the device to avoid the damaging it effectively. So this would be our set transition here. And so at this point, effectively the device is created filaments and so is now in the low resistive state. So if we now measure again, we perform another sweep, we would now realize that we are moving along this line. This is the low resistive state. And if we wanted to reset the device, I would need to reach this voltage here. So at this voltage, the filaments would be destroyed, and so we make this transition back to the high resistive state. And so this is our reset transition. And this explains, highlights how the unipolar device would instead operate. Also here, in order to read, we would apply, a small voltage down here, for example, as we've explained similarly to what we said for the bipolar device. And always remember that in the end, these memory devices have to operate with pulses, with voltage pulses. So, for example, in the case of a bipolar device, in order to set the device, what I have to do is to apply a pulse with a reasonable duration. This obviously, what reasonable means, it has to be investigated. So, but with a voltage that is above that is bigger than the set voltage that we've highlighted in our IV exploration, let's say, of the operation of the device. So I could say that the pulse I need to apply to set is, for example, here, and in order to reset, I would apply a voltage pulse that is down here. So beyond the limits set. By this reset and set transition that we've seen previously. In the case of and remember the read is we said was down here. In the case of a unipolar device, in order to set, I would apply a voltage pulse that is somewhere here. And instead, in order to reset, I need to make sure that the voltage I apply is above the reset transition that I've found here, but below the set, of course. So I need to apply a voltage that is, somewhere here. So above the reset, but below the set. And the read is always done here. So just to, write it a bit more explicitly, for the bipolar, we've said that this is the set, this is the reset, and this is the read. And for the unipolar, so this is the reset, this is the set pulse that I would use, and this is the read. So let us have a look now a bit just more in detail on how the different mechanisms work. So we've mentioned that there are three main mechanisms we want to talk about: the electrochemical metallization mechanism, or simply electrochemical mechanism. In this case, the material between the two electrodes is actually an inert material. Is not actually the reason why there is a resistance switching. But what is important here is actually the electrode, one of the electrodes. And actually the choice of the two electrodes is very important. So there is an inert electrode that is, for example, platinum, a noble metal, and a material that another electrode, the counter electrode, is actually quite mobile. It's prone to release ions that are very mobile. So this is, for example, a good candidate is silver. So what happens when we operate this device is that when we apply a voltage across this device, we may induce the migration of Ag plus ions toward the platinum electrode. They accumulate there and form a silver dendrites that then start to grow in the direction of the silver electrode, and so eventually connect with the electrode. So this creates a conductive filament. When we reverse the voltage, we reverse the process. So we remove silver ions from these dendrites that go back to the electrode, and so the conductive filament is then destroyed. So we have this transition. The set transition is represented by this creation of the conductive filament here, while the reset process, that is the destruction of the conductive filament, that is represented in this diagram here. So this is really, in few words, what is happening. Or remember that because these processes require atomic movement within the insulator in between these two electrodes, in order to happen on small time scales, what is required here is that the materials, the separation between the electrode to be extremely small, of the order of a few nanometers. Okay, so this is a very important point here. And this is actually true for all these technologies that we are discussing here. The nice thing about the resistive switching memories in general is that we can tune, because these are based on conductive filaments, we can tune with very high accuracy the resistance of the set state, of the low conductive, low resistive state. And this is demonstrated in this plot effectively for the ACM case. So you can see that the right current is actually the current that was set in order to limit the set process, if you remember. This CC current limited imposed by the instrument used to set and reset the device, to set the device in this case. So by changing the level of current allowed during the set process, we can actually create effectively filaments of different resistance. And that's what this curve is showing us. So we have the possibility to tune on an enormous range. Here you can see from 10 to the minus 4 to 10 to the minus 11 the resistance of these filaments. So when the current ranges from 10 to the minus 4 to 10 to the minus 11, the corresponding resistance of the device in this case has been seen to go from 1 kilo ohm to 10 gigaohm. So there is clearly a how many orders are these? These are 10 to the 3 ohm to 10 to the 10. So 7 orders of magnitude. And so as you can see, there is a one-to-one relation to the current used to limit the set process. The other mechanism that we would like to mention here is the VCM, so the valence change mechanism. So also here we create conductive filaments. The only difference with the previous mechanism is that here the filaments are effectively made of a phase of the active material that is much more conductive. So we can use the case of titanium dioxide, which is one of the valence change materials, valence change mechanism materials. So titanium dioxide is a relatively good insulator, let's say, but titanium can exist in many oxidation states. And so TiO2 is not the only form of oxide that titanium can form. So it's definitely the least conductive form, but there are more conductive forms, and the most conductive one is actually this one, Ti4O7. As you can see, this is the stoichiometry there effectively is pointing us to the fact that these conductive forms of TiO2 are effectively missing a lot of oxygen. So, in other words, the devices that are based on VCM rely on the fact that are oxides, and that there is the defect that present in this device is actually the oxygen vacancy. So the oxide is prone to give away an oxygen, create in such a way defects that that we would call an oxygen vacancy, and in such a way create forms, substoichiometric forms of that oxide that are more conductive. So in the case of titanium dioxide, for example, under certain biasing conditions, what happens is that oxygen is removed. You can see here in this diagram, oxygen is removed from certain regions of our active material, and so we are left behind with a growing region that is made of a substoichiometric form of the oxide, in this case Ti4O7, for example, that is much more conductive. This filament effectively can grow up to touch the other electrode on the other side, and so in the end the story is always the same. So there is always a more conductive filament that is touching than the electron, so the other electron. So the device is set in this way. And if we destroy the filament by reversing the bias, for example, we reset the devices, and so the resistance then becomes high. Here we see some practical examples of VCM devices based on titanium dioxide. Note that the set pulses here used are of the order of just 10 nanoseconds. So these devices are really amazing, and also they can be extremely small, as you can see here. So this is a TEM image of a crossbar cell made with based on titanium dioxide, I think, and you can see here the IV characteristic is clearly a bipolar device. You can see that the set transition here is happening for positive voltages, while the reset is happening here in this transition here, so at negative biases. And And finally, the last mechanism I wanted to mention to you is the thermochemical mechanism. So this is very similar to the valence change one. The only thing is that here the defects are not oxygen vacancies, but are actually interstitials. Interstitials caused by the actual metal atom of the oxide. So a material that is particularly prone to to undergo this type of mechanism is nickel oxide. So what happens in the matrix of this oxide is the nickel would leave its spot and migrate. Nickel ions would migrate in the matrix and so create interstitials, so-called interstitials defects that would accumulate and create filaments. So just to compare VCM and TCM mechanisms. So in valence change mechanism, we have a region where the entire material is changing phase. Remember, it's changing phase into a phase that probably is substoichiometric. There are oxygen vacancies, and we can demonstrate that generally this region has also a conical shape. On the other hand, in the TCM devices, think nickel oxide, because they are the filaments are based on interstitials, metallic interstitials. So we have actually here metallic filaments that are formed that may have very complex shape. But so I think it is clear that although in all cases we are forming filaments, the geometry of these filaments can be quite different. So just keep this point in mind. In terms of operation, TCM devices historically were those that were showing, at least initially, were those that were showing most than any other mechanism unipolar behavior. So it's quite interesting actually, so that's what we are seeing in this plot is the typical operation of a unipolar TCM device, where you can see also the electroforming step here in order to create the first time the filaments, as we said. This for quite some time has been seen as a drawback for this type of mechanism, mainly because bipolar is generally preferred. A bipolar operation is generally preferred over unipolar, and the reason is that in the unipolar behavior there is Joule heating involved in the reset transition, that is this transition here, that is required to destroy the filaments. But in reality, in the last few years, has become clear that actually the switching operation, whether it is unipolar or bipolar, actually depends on the size of the device. And it's been demonstrated, and this is what this slide is about, it's been demonstrated that all materials have regions where or maybe device sizes where they could show unipolar behavior or bipolar. For example, in the case of titanium dioxide, we can clearly see here that devices that have a forming current that is quite high and have sizes down to 10 to the 5 nanometer squares, they would probably show unipolar behavior. While all the other, if we use smaller forming currents and we push, the size, the device area to much smaller, we can probably be sure that we will have bipolar behavior. Something similar happens for nickel oxide. So as you can see here, all these devices show unipolar, while all the others. So there is clearly a correlation between device size and current used to do the electroforming step that define whether the switching operation will be unipolar or bipolar. And this is further emphasized actually here, where it is in this very nice diagram we actually see what we've seen in the previous slide. So clearly telling us that when we decide to scale down aggressively this type of technologies, we will probably be dealing with bipolar devices, which is good. As we said, we don't. We would like to prefer bipolar to unipolar. So this concludes our 8th chapter. Thank you again for listening, and I'll see you